Hi guys, welcome to God Academy. In this lesson, I'll be taking you through separable differential equations. In our previous lesson on differential equations, I took you through linear differential equation. So if you missed that, kindly go back to the video, do well to subscribe and you follow closely as we go through differential equation course. So separable differential equations, as the name denotes, separable, meaning we have the ability to separate, right? So have it in mind that separable is simply saying something which has a tendency to be separated. Okay, what are we separating? Now let's analyze this. The general standard form for different separable differential equation is given as a function n of y multiplying dy, and this is equal to a function m of x multiplying the x. If I have any differential equation and I'm able to separate all my y's on one side attached to the dy and also separate all my x at one side attached to the dx, then it means that I have a separable differential equation. As simple as that. So our goal is group all y's at one side, then group all x at one side, attaching the respective derivatives so that you can perform the necessary integration. Once you have expressed your differential equation into the standard separable differential equation form, you only have to integrate. So this will be integral of n of y dy should be equal to integral of m of x dx. So the result of this integral becomes a solution to our separable differential equation. Let's take one example and see. So this example, I have dy over the x is equal to 6y squared x. The y over the x is equal to 6y squared x. First of all, we've been given a question like this, a problem like this. Before you start to solve, you ask yourself by analyzing what you have here, okay? Now, for you to easily identify separable differential equations, the dominant operation within the differential equation given should be either multiplication or division. Take note of these two. So it's either it is multiplication or division. Once these two are the dominant operation within the differential equation, it means that separation is going to be very possible. Operations like addition and subtraction mostly prevent us from separating effectively, but still let's see. So with this example given, you can see that 6y squared and x are simply multiplying. So it's easier for me to cross and separate, right? So that's easily what we're gonna do. So with this problem, I simply cross multiply as the first step. I'll have dy is equal to dx multiplying 6y squared multiplying x. The goal is to group all y at one side attached to the dy and to group all x attached to the dx. So the dy and the dx remains as it is. But we have to make sure each variable here moves to the corresponding dy or dx. Because of that, I need to make sure I get rid of my y to my left side by dividing through by 6y squared by 6y squared. This simply eliminates 6y squared here. Then I'm going to be left with the expression dy over 6y squared is equal to x dx. Is that not it? So we can say that 1 over 6y squared dy is equal to x dx. Now we have successfully separated our differential equation. The next thing is to solve the differential equation. To solve, we simply introduce our integrals on both sides, okay? So observe closely. I have integral of 1 over 6y squared dy is equal to integral of x dx. When you have an integral of 1 over 6y squared, how do you solve this? Whenever you are about to solve any integral, first thing first, push every constant outside the integral sign, okay? So we're going to have 1 over 6 outside integral 1 over y squared, okay? We have the y is equal to integral x dx. Now we move forward to solve it. When you have y to 1 over y squared is the same as, take note, 1 over y squared, let me solve it here. 1 over y squared is the same as y to the power negative 2. Is that not it? Integration is simply saying that add 1 to the power, then divide by the result. So this integrated will be y to the power negative 2 plus 1 all over negative 2 plus 1. And this gives us y to the power negative 1 over negative 1. Is that not it? So it becomes negative 1 over y. Let me come back to my integral. So I'm simply going to have 1 over 6 multiplying negative 1 over y plus c is equal to, when you integrate x, it becomes x squared over 2 plus c. Please, whenever you are doing separable differential equation, don't repeat constant. Choose only one. So let's get rid of the one on our left side, okay? So let's get rid of this and maintain only this. It doesn't change anything. So our equation then becomes negative 1 over 6y is equal to x squared over 2 plus c, simply like this. At this point, we call this solution implicit solution. Implicit, okay? Implicit solution. It's implicit because we have not made y the subject. Once we make y the subject, we get what we call explicit solution. Explicit solution, okay? And that becomes the gold standard. So it's not every equation that you can convert it from implicit to explicit, okay? But this is possible. How do I do that? So I'm going to have negative 1 over 6y. Remember, this is a general solution because we have c. The constant has not been replaced by the actual value. So this is a general solution, okay? So I have negative 1 over 6y is equal to, so let me solve it straight away here. So this, to make y the subject is very easy. Just somersault it. I'm going to have, or I can even crosswise. Okay, I'll have negative 1 over the expression x squared over 2 plus c is going to give me 6y. Is that not it? And you simply divide through by 6. So, but even at this point, it's enough to some problems. Okay, so therefore we can say that y is equal to negative 1 all over 1 out of 6 outside brackets x squared, sorry, not 1 out of 6, 6 actually. You're dividing by 6, so I have 6 outside x squared over 2. Let's see, as simple as. So this is a typical separable differential equation that we've solved here. Now let's see this. Let's solve this second example and see. So with our second example, I have the expression y prime is equal to e to the power negative y multiplying 2x minus 4. I have initial condition saying that y of 5 is equal to 0. This is a boundary condition, not initial, okay? Boundary condition. So this is our second problem for the separable differential equation. To solve this problem, as I said, you should first identify the operations which is dominant. Looking at this, you can see it's multiplication, right? There's only one minus, and therefore I can see my y is obviously separated from my x, hence it's separable. The first step is to convert this to dy over dx for clarity. Okay, it's equal to e to the power negative y multiplying 2x minus 4. At this point, you just cross multiply. Okay, crossing multiply, I have dy is equal to the x multiplying the expression e to the power negative y times 2x minus 4. As simple as that. Okay, once you have this, as I said, all y's should go on one side and all x should go on the other side. But the y's should be attached to the y and all x should be attached to the x. Okay, so we're going to have this whole expression divided by e to the power negative y and this whole expression divided by e to the power negative y. So what do I get here? Remember, e to the power negative y, when I want over this expression, simply gives me e to the power y dy. Okay, is equal to, if you didn't get that, you have 1 over e to the power negative y, the same as 1 over 1 over e to the power y. It's somersaults plus e to the power y, as simple as that. This should be equal to 2x minus 4 dx. Now we have successfully separated. The next thing is simply attach our integral signs to this. Okay, so when I have integral of this, what do? We solve it simply. Integral of e to the power y dy is the same as e to the power y. It doesn't change. Go and revise your integration. Integral of this becomes x squared minus 4x plus c. Okay, remember we were given a boundary condition that the value of y at x equals 5 is 0. So we place that in nicely. So meaning y here becomes 0. I'll have e to the power 0 is equal to 5 squared minus 4 times 5 plus c. E to the power 0 is 1. This is 25 minus 20 plus c. So you can see that I'm going to have 1 equals 5 plus c simply equal to negative 4. Therefore, my particular solution becomes e to the power y is equal to x squared minus 4x minus 4. And that is the solution to this differential equation. This is the implicit solution because we have not made y the subject. To write the explicit solution, you have to take ln on both sides. So I'm going to have ln e to the power y is equal to ln of the expression x squared minus 4x minus 4, right? This becomes y is equal to ln x squared minus 4x minus 4, and that is the solution to our differential equation. So this is all about separable differential equations and how to solve separable differential equation wherever you see it. Okay. Now let's go to the next type of differential equation, which is which I'm going to take you through. Right. Let's do exact differential equation. Exact differential equation. What do you mean by exact differential equation? Okay. So generally, if I have a function of x and y is equal to an expression, okay, or any function which has more than one independent variable. What I mean is, if a function depends on more than one variable, then we have what we call partial derivatives. Partial derivatives, okay? Derivatives, okay. So now, this is it. I have a function of x and y which is equal to 2x plus what 3y. This function here will get its value when we know the values of x and y at the same time. The value of x is not enough to get the value of this function. Every function performs a particular task, but it takes an argument. Argument is simply the x and the y you see here, meaning that we need two different values to make this function functional. That gives rise to the partial derivatives. So now this function, if you want to differentiate this function, we will differentiate it in parts. Okay, in parts, because it depends on x and depends on y. So the total derivative of this function as the f of xy over the xy is simply equal to the partial derivatives of the f of xy. You see the partial derivative sign over the x plus the f of xy over dy. So it's like we have broken it into parts. So each derivative is called a partial derivatives. This is where I'm drawing your attention to. Differential equation is simply finding the inverse or trying to reverse an equation from a derivative form to its normal form. There are so many types of equations and so many types of expression. Depending on the type of expression, that will determine how we should reverse it. So mostly for exact differential equations, what we are interested in is we are interested in the fact that we have two different parts, the x component and the y component. So we don't just go by one way. So let's see how it is done. Generally, exact differential equation has got a form m of xy dx, right, plus n of xy y is equal to 0. Have this in mind. You know that separable had mx and ny. Here, each component has got x and y, okay? But there is the x and there is the y is equal to 0. So the function which gave birth from the derivative, partial derivative with respect to x is this one. Okay, is the m side. Then the function we gave birth to the partial derivative of the y is the n side, and it should be equal to 0. Let's take a problem. But before we take a problem, we always test for exactness. So let me write this here. Test for exactness. Meaning that you have to make sure the equation is indeed exact before you proceed. How do we determine that an equation is exact? For you to determine, have you seen this m? So our general form is mostly represented as mx plus ny is equal to 0. Mx because this is from the partial derivative with respect to x and this with respect to y. For the test of exactness, it says that mxy should be equal to nyx. Yes, this is a mathematical language. What it's trying to say is differentiate your m part of your equation with respect to y and differentiate your n part with respect to x. It's like the inverse. We realize that the m part is attached to the x, but we have been asked to differentiate it with respect to y. That is the opposite. Differentiate the n part with respect to x. That is the opposite, and they should be equal. Once this condition is satisfied, it means that our equation is an exact equation. Now let's solve an example for you to understand it better. I have this expression here: 2xy minus 9x squared plus 2y plus x squared plus 1 dy over dx is equal to 0. Okay, now this equation that I have here is what we've been given to solve. But before we even start solving, we ask ourselves that is this an exact differential equation? How do we determine that? It's clearly seen here that this side is our m part and this side is our n part all the time. So mostly where your dy over the x, or when I cross multiply, you see that the x will come here, right? It's your n and this is your m. Okay, so let's break our function into two. So our m of xy is simply equal to 2xy minus 9x squared. Is that not it? Then our n of xy is simply equal to 2y plus x squared plus 1. The test says that we should find the m of xy dy. We have rather differentiating the m part with respect to y. Let's see what we are going to get. When I differentiate this with respect to y, any component, any variable that is not y, is a constant. So 2xy, when I differentiate, 2x is a constant. It remains 2x. I don't touch it. But when I differentiate y, it becomes 1. Therefore, my answer is 2x. 9x squared here, everything, there is no y component here. So it's a whole constant. So it's 0. Please take note. We are differentiating it with respect to y. Change of y. If there is no y, it means 0. This is gone. So our answer is 2x. Now let's come to the end part. Here we are rather differentiating with respect to x, though it is attached to the y. So it's the opposite. Differentiating with respect to x, the first term is 2y. 2y is y, but we are differentiating with respect to x. It becomes 0. It's a constant. The second term is 2x. 2x, sorry, x squared. When you differentiate, it becomes 2x. Is that not it? 1 becomes 0. Therefore, 2x and 2x are the same. We can say that our equation is said to be what? Exact. Once you have confirmed that our equation is exact, now comes the actual solution of our differential equation. How do we solve exact differential equation? Let me show you one easy technique. The first technique is that you will integrate your mxy with respect to the x separately and integrate your nxy with respect to the y separately. Then after you merge them. That's all. As simple as that. Let's do that here. So my mx of y, so integral of mxy dx, how do I do that? I'm going to have integral of 2xy minus 9x squared all x. So when I integrate this, what am I getting? Let me remove this. This becomes, with respect to x, please take note. If you are differentiating and integrating with respect to x, you don't touch the y part, okay? So my y becomes stagnant, okay? My 2 becomes stagnant, it's a constant. By my x becomes x squared over 2. So if my s become x squared over 2, it will take away these two. Is that not it? And I'll be left with what? S squared y. Here too, I'm integrating with respect to x. This becomes what? You add 1, becomes 3. To become minus 3s cubed plus c. You put it down. Let's do integral of the n xy dy. What do I get? So this integral of 2y plus x squared plus 1. Is that not it? Dy. Integrating this expression, what am I getting here? So let's circle this as our first solution. Okay, this is our first solution, like this. So for this one, we are going to get, I'm integrating with respect to y. So this gives me y squared. Is that not it? This gives me, this is x squared. There is no y term. So here we don't say it's a constant, it's going 0, but rather y appears. So this gives us y x squared. Please take your integration serious when you're doing differential equation. Then 1 becomes what? Plus y. As simple as that. Okay. At this point, this is our second solution. And I told you that we are going to merge them. To merge this solution, we are going to make sure that we are going to combine them, but we avoid repetition as much as possible. So therefore, our differential equation, generally a function of x and y, will be equal to the first one. Here I have x squared y. I write my x squared y down. The next term is what? When I come here, I have x squared y here. So this and this cancel to give me only one. I'll take only one. I have y squared here plus y squared is also gone. I have minus 3s cubed here, minus 3s cubed. Then I have what? Plus y, plus y. And that becomes my solution to differential equation, as simple as possible. And that is all about exact differential equation. But let me show you the actual way we could have solved this problem. Okay, so instead of us trying to use this shortcut, but I think I recommend this method to you because it helps a lot. Okay, it helps a lot. So now what I'm trying to say is, have you seen when we found our m, this one, when you integrated the m part or n part, for you to solve, we only used one of these. But here, instead of plus c, so let's see something. The first step is you will integrate your m of xy dx. But here, your constant of integration doesn't become a c, but rather a function of y. If I go by the nxy approach, when I get my solution, my constant of integration doesn't become c, but it becomes n of x. I don't know if you get it. A function of x as my constant of what? Integration. Let's see. Now going by the mxy, let me take this section. I'll have what? My solution was s squared y minus 3s cubed 3s cubed plus what? Now becomes a function of what? Y. As I'm saying, what we are doing here is an implicit function. It has a component of x and y. So if you differentiate only the x part, what is left is not a constant but the y part. Okay. So at this point, this is what I've gotten. So now this expression here is assumed to be the actual differential equation we are looking for. Okay. So this is equal to our differential equation with respect to y. General equation. But for us to get h of y, we need to what? Differentiate this whole expression with respect to what? Y. Is that not it? So differentiating this whole expression with respect to y, what are we getting? We are going to get here, with respect to y, I'm going to get x squared, right? This becomes 0, it goes away. Plus, differentiating with respect to, I'm going to get h prime of y. And this is going to give me the y component of this, and that y component is the same as the nx of y, which we've been talking about. So we'll go back to our equation and you see that the n component was given as what? 2y plus x squared plus 1. So here you replace what you have down here plus here. Now this part of the function becomes 2y plus, is it x squared? Yeah, 2y plus x squared plus 1, because we have differentiated our general function with respect to y and we expect it to be equal to the y part given from the main question. That's um the logic behind solving any exact in the normal way, aside the first one that I showed you. Because of that, at this point we need h of y. That is the goal. So what do? We make sure that we simplify. Simplifying this becomes a differential equation on its own. So I have h prime of y is equal to my x squared, and x squared will go. Is that not it? I'll have here 2y plus what? 1. Then I take integral because I need h of y. So integral of h prime of y should be equal to integral of 2y plus 1. Is that not it? So I'll have h of y is equal to, when I integrate 2y, I get y squared plus y. Then it means that we are done. When I come back to my equation, you realize that here, this is where we left, right? Where is it? Yeah, this is it. So this is what I was talking about. So at this point, you have found the value of the answer for h of y. So we just come and replace it into the function. So our function becomes s squared y minus 3s cubed plus y squared plus y. And that was the same as what we got here. Is that not it? And that is it. So this is the end of our section for this tutorial. I'll see you in the next lesson. Kindly subscribe to support this community. Thank you.